All right, hi everyone. Today we are doing derivatives, but we're going to do it the fast way. So we're going to compare the old way versus the new way. And there's no way to do it the old way anymore. Old way, let's talk about the old way versus the new way. So our classic way, our limit way, limits, and we wrote it as limit h approaches 0 of f of x plus h minus f of x all over h. Oh, that's ugly. Okay, that's the idea. That's what we took. And we said this was another way of writing slope. Our slope equation from algebra 1 is y2 minus y1 over x2 minus x1. Right? And the idea of this was rise over run. Easy peasy, right? And the problem with this is you needed 2 points. But whenever you draw 2 points on a graph, those 2 points end up giving you what we call a secant, which is not really the slope of our 1 point, but slope of 2 different points. So we said, what if we move this secondary point here super close to the first one? So close that they're sitting on each other's laps. And that's where this aspect of h approaches 0 comes in. What if the x's, x2 minus x1, were so close together that it was practically 0 spaces away? 0 spaces away. But when you did that, you also made the h up here 0 spaces away, and it may give you a 0 over 0, which makes sense. It's the same freaking point. If you wrote y2 and y1 as the same y2 and y1 point, it would just be 0. Like, why are we doing this? But it turned out, from pre-calc, that was a hole. And that allowed us to then simplify, get rid of the h, and still come up with an equation. Now we're going to do that right now for a power of x squared. And we did this before, limit. So we'll say f of x is equal to x squared. And as h goes to 0, of x plus h squared minus x squared over h. If you need the assist, the x plus h version is x plus h squared, okay? That's the assist. And that's how we wrote this, like right there. All right, so we went ahead and, okay, I'm just gonna go slow here. If I plugged in a 0, we would end up with x squared minus x squared over 0, which is 0 over 0, which is what we don't want. So we go ahead and we said, okay, multiply it out and see what happens. Find another way. The limit as h approaches 0 of x squared plus 2xh plus h squared. Remember, squaring a binomial, square the front, square the back, double the middle. Minus x squared over h, blah, blah, blah. We see that x squared. Another hint that whenever you get rid of your common values, you should always be left with h's left. Everyone should have a pass to the after party. It's 2x plus h. Oops. Okay. So I want to factor out the h here because I can. And we can see that we do have a common h that divides out. And this, ladies and gentlemen, was our 0 over 0. Remember, this was our 0 over 0 that we wanted to get rid of. See you later, hole. Stay holy. And this gave us the limit h approaches 0. As you notice, I kept writing limit, limit, limit this whole time because I haven't plugged it in yet. I've been holding myself back, restraining myself. And we're at 2x plus h. Now that we got rid of our 0 over 0, we can now freely plug in 0. So it's 2x. So what does this mean? This idea here is that this is the slope for f of x equals to x squared. This is the change. Okay? The slope, this is the change. So this is a good thing because there is a pattern. And if I did the same process for limit h goes to 0 for f of x being x cubed, we could set it up x plus h cubed minus x cubed over h. Same process. I could tell you, you end up with 3x squared. I'm not going to do it. I mean, we could do it, but let me do one more. Limit as h goes to 0. What about for f of x is equal to x to the fourth? X plus h cubed, to the fourth minus x to the fourth over h. I could do the whole problem out. I'm telling you, pattern's going to be this. So the rule I'm describing now is what we call the power rule. Now, the power rule is one of our basic derivatives for us to remember. And it really is a pattern and allows us to skip this huge limit step. Now, let's go ahead and set it up. Now we are going to write, this is the power rule. If I want to take the derivative, so I'm going to give you guys some new notation here, just some FY. So just notation on the side. I say y is my function, then the derivative is written as y prime, or the slope of y. If I write f of x, the derivative is f prime of x. What if I give you a different letter? Call it h. The derivative of h is just h prime. So a common notation is that once I put a little apostrophe there, now it is the derivative. It is the first slope. So from now on, you can use the power rule for your test, not on our last test, but from now on for all future tests. Good question, Finn. So here's our power rule. So if x to the n, so let's write f of x, let's write nicely. F of x equals to x to the n. I'll write nicer. If f of x is equal to x to the n, okay, which is a polynomial here, then f prime of x is equal to n x to the n minus 1. Let's show that on the examples we just did before. If f of x equal to x cubed, f prime of x, the derivative, would be 3. So we take the exponent and we move it to the front, which is what we did there. And then we subtract 1 from the exponent. Look at the pattern again. Right? Okay, so that's another rule. We're going to use this same rule. But let me finish this one, and we're going to get there. Good question, though. If I said x to the fourth, the derivative is bringing the exponent to the front, 4, x, and we minus 1 from the exponent, comes a 3. Yeah, Lena. That's right. So this is the power rule. This is one of the cool derivatives that we learn to make our lives so much easier, so I don't have to do the limit rule. So you can say, Mr. Ko, we did all this work before. What's the point? And as I mentioned before, if you don't see it the limit way, you don't see it that it's really just the slope. This equation here is really just a modified version of slope. You do not see that in the power rule. The power rule is it's a coincidence. It works. And this rule works all the time. So I need to say that if you had learned this to begin with, it's just a made-up rule. There's no correlation. Now, this only works because the limit definition works. That's the only reason why it works. Have you ever heard your parents say, because I said so? Why do we do it this way? Because I said so. It's totally made up, okay? But this rule isn't totally made up. This rule is made because it so coincidentally follows the limit rule. Okay, so here are a couple other rules that we need to know when it comes to limits before we come back to power rule. Because if this is the only tool I have, what about, like what Yitzchak asked, about what if there's a constant in front? So here are a couple of derivative rules. Here we go. Okay, we have a constant multiple. Okay, the constant multiple rule is if I say 3 times f of x, okay, the derivative is 3 f prime of x. What I mean is the constant just sits there and watches everyone get rich. Okay, here's my example. If I wrote 3x to the fourth, this is 3, and then we take the derivative of x to the fourth, which is 4x cubed. Please notice that the 3 is a constant. It just sits out while the derivative is taken. If I give you another example, x to the fifth over 2. Okay. Well, the derivative of this would be, sorry, this should be an arrow. The derivative of this, let's rewrite this as 1/2 x to the fifth. And the derivative of this guy is 1/2 5x to the fourth. So as long as it's a constant, it can just sit out on the sideline and just watch me play. But how did they come up with it? Oh, it's based on the limit rules. If you guys remember this from before, the limit of, let's say, x equals to a of k of f of x is k limit as x goes to a of f of x. The constant value just get kicked out. So it's based on our previous limit rules. Because the derivative is just a limit. Okay, so I'm gonna throw this in there. What if I gave you this? Here's a definition of another derivative that you have to memorize. The derivative of sine x. So the derivative of sine x. So another way for us to write a derivative now is this notation, d over dx of sine of x. This is derivative. Oh darn it, that looks ugly. Derivative of sine of x with respect to x. Where did I get the x from? From this notation right here. This x refers to this guy here, the dx. So this rule is cosine of x. The derivative of sine is going to be cosine. I will explain that out later in another class. I'll draw it out. It's pretty cool. But just right now, just to say this is a true statement. We're just going to use it. If I gave you 72 sine of x, and I asked you to take the derivative of 72 sine of x. Well, x is my variable, so 72 is a constant. This is just 72 derivative of sine of x. What did we say the sine of x was? we said the sine of x is just replaced with a cosine of x. The point is that if you have a constant in front, just leave it. Worry about stuff with a variable. Okay. Some other examples of power rule. Okay, some other examples of power rule is pretty much every type of a value you saw in Algebra 1. So let's look at some other common examples. So what if I wrote 1 over x squared? What is the derivative of 1 over x squared? So again, I want to write this in a very different way, slightly, so you guys can understand what I'm talking about. When you see the word d, that means the derivative. That's an easy way to think about it. Like, it's a derivative. It actually refers to like the difference, but this derivative, that's the derivative. So I'm taking the derivative of 1 over x squared with respect to dx. That's our idea of writing it, okay? Me writing it in front means the same thing as me writing it in this funny way here. This can also be rewritten in some places as, for instance, d of f over d of x. In Algebra 1, we might treat this with d of y over d of x, because isn't f the same thing as y? So the idea here is the derivative of y with respect to x. Yep, you guys did learn this somewhat in last year probably from your teachers. Okay, so let's go back and talk about our initial problem here. The derivative of 1 over x squared. So that's not a power, or is it? If I rewrite this using my rules, can I rewrite this as x to the negative 2 power? I can write it on top, but with a negative exponent. Hopefully you remember that. If you don't, nope. So if I want to take the derivative of this guy, now it's just a power rule. Let's go ahead and do the power rule. Power rule says this is negative 2. X to the negative 2 minus 1 is negative 3. And this turns out actually to be our derivative. Let's do another one. It's d over dx of 5 over x cubed. 5 over x cubed. So let's rewrite this with a negative exponent, please. 5, x to the negative 3. We learned that constants don't matter, so please wait outside the store while I do my business. 5, and the derivative of, sorry, whoops. This is wrong. I wrote the wrong notation. I didn't write d over dx. I forgot to write it. Okay, I forgot to write it. You have to keep writing it, just like limits. If you haven't done it, gotta keep writing it. And then we're gonna do our derivative rule. And it's negative 3, x to negative 3 minus 1 is negative 4. If you need the little note, write this on the corner just for yourself, to remind yourself, negative 3 minus 1 is not negative 2. This is negative 4, not negative 2. Some people go the other way. Okay, we can simplify this. 5 times 3 is negative 15 here, over x to the 4th. Okay, let's move on. Any questions on these fractions?
Wait a minute.
Oh, yes, Naman?
Why is it over x to the 4?
Because see this negative exponent here?
Mm-hmm.
Where does it really belong? On the other side of the street. You don't belong here.
Yeah.
You go back to your side. Okay. Wrong side of the streets. Some people might not like the negative there. Maybe negative 15 over x to the 4th might look a little better too. Okay. All right, let's do one more. Let's do one more rule. And this again, it's another exponent. Doesn't look like it though. D over dx of the square root of x. Square root of x. Can I write the square root as a exponent? Oh boy, oh boy,
Yes.
oh boy. What's my exponent?
Half.
Half. Thank you. Good job. Summary wasn't that long. Okay. So 1/2. Then we treat this just like any other exponent. So we copy the fraction to the front, because that's the exponent moving it to the front. And we subtract 1/2 minus 1. 50 cents minus $1 is you owe me 50 cents still. So rewriting this, 1/2 square root of x. Mr. Ko, can you move the square root to the top? In calculus, you can leave it. Leave the square roots there. No one gives a crap. Leave it. Finally, Mr. Ko, why did you learn that in Algebra 1? So that's it. Turns out that that's actually the derivative. And what that means is this is the slope equation. These are all the changes of my square root of x graph. I can predict you what the slope is. You just give me an x. So I want to actually illustrate this with this version here. So if I graph a square root of x graph, and please, whenever you graph square roots of x graphs, please plug in numbers that you know the square root of. Like, don't plug in square root of 3. Who the hell knows what the square root of 3 is? What is the square root of 0? 0. What's the square root of 1? 1. What's the square root of 4? 2. So please, really, don't plug in dumb numbers. Okay? Now, here's what we're going to do. We're going to actually figure out what the slope is. So at x equals to 1 and 4, we're going to figure out what the slope is. I want to see if this does predict how fast this graph is changing. Now, imagine if this was money. You increase a lot, and then you start to taper off your growth. This is like your height for some of you guys. In junior high, you shot up, and now you're a senior, and you're like, I'm still growing. Yeah, you are. Sure, I'm still growing. I'm not growing vertically, though. I'm growing horizontally. Okay? It's not a good growth, man. I'm telling you. Okay. Life after 28 is not good. Just FYI. So as you can see, the graph actually tapers off, and we don't grow as the change isn't as strong. And our derivative here is going to show that. So let's go ahead and plug in what is f prime at 1. See, this means what is the derivative at x equals to 1. Okay, so we're going to go ahead and plug in our derivative. It's 1/2 square root of 1, which is 1/2. If I draw a tangent line here, rise over run, that's like 1/2. Yeah, that looks pretty good. I fudged it pretty well. Okay. So if you look at my tangent line at 1, that's at 1. Rise over run. The rise over run is changing by 1/2. Yeah, I fudged that pretty well. So as we continue, do you think the slope is going to increase or decrease? Is the change going to get stronger or weaker? If this was a stock market, over here, whoops, wrong one. This would be more of a flat graph. Okay. So I'm not as strong as I was before. So let's see what it looks like at 4. If I go ahead and plug in 4, what is the slope? F prime at 4. What would the slope look like at 4? What would the change be? Would the change be would be stronger or weaker? And that's 1/2 times 2, which is 1/4. Rise 1/4. Rise 1, 1, 2, 3, 4. Fudged that pretty well too. And as this graph progressively gets farther out, if I plug in 9, this number is going to get f prime at 9 would be 1/2 squared of 9, which is 1/2 times 3, 1/6, which is a smaller number. And that's right. At 9, the graph would grow even less. We go from a 0.25 growth, 0.5 growth, 0.5 growth to a 0.25 growth to a whatever 1 divided by 6 is, like a 13 or something, 0.13 or something. Okay, so my goal is to show you that the derivative does illustrate the change. And remember, calculus was created to describe physics. And physics is all about how things are changing. Velocity, what they call kinematics, study of movement, talks about how position, velocity, and acceleration are related to each other, because velocity is just a change in position. Acceleration is just a change in velocity. And it turns out this is all super related. And calculus was created to describe physics in the numerical sense. Okay. Let's go ahead, and now that we've learned the 3 different types of derivatives that we talked about using power rule, basic, let's go back and review quickly. Basic exponents, basic exponents, right? Just what if it's x cubed? Easy. What if it's written as a simple fraction? We can write it as a negative exponent. Got it, easy. What if it's a square root? Change that to a fraction. Got it, easy. Okay, let me do one more as a square root real quick since we're here. If I say d over dx of the cube root of x squared. Just as a reminder how to write this exponent. This is the same as a derivative, d over dx of, so the derivative of x 2 out of 3 with respect to x. Okay. 2 out of 3. Now, if you don't know how that works, let me help you out just on the side in case you need some algebra 1 help. If I wrote square root of x cubed out of 3, you'd agree I have a set of 3, and this comes out as 1x. As a reminder, how does that work exponent-wise? I have 3 x's out of 3. Well, that becomes x to the 1, as we can see here. Just to help you guys out, in case you don't remember the rule, if I write the cube root of x to the 5th, I have x 5 out of 3. I'm counting by 3s. This leaves me with 1 whole and 1 with 2 left. Oops, sorry, that should be an x. I don't know why. That's an x. The whole one becomes a regular x on the outside, free of square roots. And the other one is stuck with 2 left over. Just to help you guys hash this out if you guys don't remember how to do the exponents. Okay. So what if we had the 2 out of 3 here? Follow the power rule. Exponent always gets written in the front. That's 2 over 3. I do not write derivative anymore because I'm doing the derivative. X and 2 over 3 minus 1. I'm going to save you guys a step here. Please do this. It'll save you some time. Instead of writing 1, write that denominator. Isn't 1 just 3 over 3? The same thing. Just write 3 over 3 instead. It'll save you a lot of brain power. And we're left with negative 1/3. Rewriting this, it's 2 over 3 on the bottom, and we have 1x out of 3. We have 1x out of 3. You're no way coming out. Okay, just help you guys out in case you needed that help. Now, our next limit rule, we talked about the constant multiple. I want to talk about another rule before we jump into applying more of this stuff, is the derivative. So let me move it up so you guys can see in case you need that.
Wait, mister, I have a question.
Yes.
What happened to the negative on the 1/3?
So remember, it's an exponent, right?
Mm-hmm.
And exponents as negatives don't belong here on top with us, cool people. You go back down there, mole man.
Oh, yeah, okay, yeah.
Okay.
Thank you.
It's like little badge that says you're not from around here. You're a visitor. Visitor badges. Get out. Good question, though. because probably other people are confused about that. So, and just remember, I have 1x out of 3, so I have 1x out of 3. All right, so our next rule is derivative of constants. And these are just numbers themselves. Like, what is the derivative of the number 5? So I would like to say this a couple of different ways. Let's say this is y. The graph y is equal to 5. Let's graph that on the right side here. 1, 2, 3, 4, 5. Here's my graph of 5. That's y is equal to 5. To remind you, what is this idea of a derivative? What's the idea of a derivative? Jumping all the way back up here, we said the idea of a derivative was, I didn't write it. It was about change, remember? It's about slope. It's about your rise over your run. That's what a derivative is. How much have we changed? Well, folks, imagine if when your parents left the house, you're sitting on your chair in your room in front of your computer. When they came home, you're still sitting there. Haven't moved, still sitting there. It's midnight, you're still sitting there. Have you changed? Andrew, have you changed at all? Just kidding, Andrew. So there's no change. That is 0. It is always 0. The derivative of a constant, no variable, a constant by itself is always 0. Because the idea of a derivative is how much you're changing. But if you're stuck at 5 feet and you've been 5 feet for the last 3 years, I'm sorry, you're stuck at 5 feet. There's no change. Okay. So now that we know what the derivative of, so these are different. On the side, if I say another example, bad, okay? If I write d over dx of 5x squared, is y a constant? No, it changes whenever x does. This graph is not a constant. This graph is not a constant. So we know it's going to constantly change on us. So we can see the difference. Okay, so we are going to mix these together. Now, this is our addition and subtraction rule now. Addition, oops, and subtraction. Addition and subtraction rule for derivatives. Oh, that looks terrible, almost. So one of the cool things is that if this rule works out, your life is easier. If this rule works out, your life is easier. Because the rule says this. If I say d over dx of y1 plus y2. You guys all see how this is an addition problem? I'm just adding 2 separate problems. Here's a real blunt way of saying it. It's just the derivative of them separately. This is not a distributive property. Don't think of, let's go, we're distributing. No, it's just the rule. I'm giving you the rule. A derivative of 2 things that are being added or subtracted is the same as us taking a derivative of them separately. Because if I give you this example, what is the derivative of 5x squared plus 5? Okay. A derivative of them together is the same as a derivative of them separately. So this is really a derivative of 5x squared separated by a derivative of 5. Will you have to write this all the time? No, please don't. I'm just trying to get your brain into it, saying that these are separate problems. Whenever you see a plus sign, that's a win. It's 2 separate problems. Do them separately. So to do this problem, let's go ahead and use all our rules. This is a constant multiple because I have a constant of 5. I'm going to write it out. You don't have to, like, eventually, but I'm going to write it out. Whoops, sorry. Let's write it as 5d over dx of x squared. See how I kicked out the 5 because it's a constant? Excuse me, your kid, can you put him outside in the car? Thank you. The 5? Hey, we know what the derivative of 5 is. That's nothing. Constant. Constantly annoying. Oh shoot, sorry. I'm on mic. And then we know what the derivative of x squared is. Power rule. So bring down the 2. Bring down the 2. All the way down. And then we minus the 1. Oh gosh, last time I made jokes too much. So this is actually 10x. Okay, talking about walking out all the rules. You should be doing the rules in your head. A derivative of two things are adding, easy. Just take a derivative of them separately. Oh shoot, there's a 5 in front. That's a constant. Ignore that. We'll deal with you later. Just sit on the side. We're gonna take the derivative of what's important here. That's 2x. Then we can bring it back in afterwards. Now, here's the cool part. Don't do this anymore. Once you get it stuck in your head, you go from here to here in one step. So when it comes to the constant multiple, where was the 2 going to go? Wasn't it going to go in the front anyways? Yeah, but someone's there. So 5 times 2 is 10. 2 minus 1 is 1. What's the derivative of 5? 0. Done. If you don't like me, I could do this the limit way, and it would give you exactly the same answer, except with half a page of work. You have to show as much work as you need to. In this case, since it is a super easy derivative, no work is shown except the start and the finish. But limits are only this easy for like the first section, right? They get a little more complicated and you're gonna have to show work. So let me give you guys another one. D over dx of, okay, I'm gonna give you one real quick. What's the derivative of 5x, not x squared, okay, 5x. This is the same as, take out the 5, and what's the derivative of x? Now, I want you guys to look at this real quick. So this is a way of looking at it. What's dx divided by dx? Shouldn't they cancel out? That's just 5 times 1, right? Okay, that's one way of like algebraically looking at it. That dx is some value divided by dx. They should cancel out. Now I'm going to show you guys the power way. Here's the power way. 5. What's the derivative of x? Okay. So the derivative, take a look. Exponent is 1. Where does the 1 go? In the front. So this is 5 times 1. And what's 1 minus 1? 0. So please take a look. Whenever you take a derivative of just an x, it actually turns out to go away. The x goes away. And this is the answer is 5. Just on the side, let me do this again, just so you see it. I'm going to erase this just to help you guys out. If I say d over dx of 6x, okay? This is really 6. What's the derivative of x? To do the power rule, okay? If you want to do it, that's a 1. Bring the 1 to the front. That's 1 x to the 0 power minus 1. This is really just, sorry, forgot the 6. 6 times 1, which is 6. Okay? This only works if it's just the variable x. Now, I want to show you the dumb way of doing this. If I wrote y is equal to 5x, what's the slope of this graph? 5. That's your answer. Okay, that's a classical algebra 1 idea because a derivative is just a change. It's just a slope. So what is the slope of 5x? It's just 5. So what's the slope of 6x? That's just 6. So the rule is, here's the fast way. Any number of x, if I take any derivative of a constant with an x, that's just a constant because that's the slope. Okay, now knowing this rule, if I write, here's our big derivative. If I write x squared plus 3x minus 1. Okay, so the long way to make sure we got this. A derivative of addition means a derivative of the parts. So derivative of addition or subtraction is a derivative of the parts separately. Bam, bam, bam. Okay, 3 different parts. Derivative of x squared plus the derivative of 3x minus a derivative of 1. And we're going to use all the rules we just talked about to solve this problem. A derivative of x squared is the power rule. This is bring down the 2. X, the 2 minus 1 is just a 1. You don't need to write it. A derivative of a constant and an x, that's just a constant. And the derivative, hello? Oh, okay. The derivative of 1 is just 0. So you don't even have to write that. The derivative is 2x plus 3. 2x plus.
We can't hear you, Mr. Ko.
Okay, so why is this beneficial to us? Because if I know my rules for derivatives, these derivatives actually are super fast, especially if it's just a polynomial. So I'm going to do another one. Ready, get ready. It's going to be 1 over x squared plus 3x squared plus 4x. Okay? I'm going to make your life a little easy. The first thing you should do is change that x squared on the bottom. This is going to be x to the negative 2 power. You guys feel okay about that? X to negative 2. Rewriting it. So this is really this problem here. And then next step is just this. If you need the help, please write the negative 1 next to that negative 2 exponent to help you remind you you're not adding, you're subtracting. That's why you're going to negative 3. So the whole exponent gets moved to the front. That's why we have a negative 2. The square goes to the front. That's why it becomes a 6. And the 4x is just the slope of 4. Okay. If you want to mix them all together, you can write, oh, let me give you one. If I give you d over dx of x squared plus 3x plus 2, all divided by 5. Hey, write it this way. It's the derivative of 1 over 5 times x squared plus 3x plus 2. You can also see I took the 1 over 5 out. Since 1 over 5 is a constant, and derivatives kick out constants, this is really 1 over 5. When you take the derivative of everything else, which is just 1 over 5, 2x plus 3. If you want instead, let's go through a different path. If I write it as 1 over 5 x squared plus 3 over 5 x plus 2 over 5. Okay, if you notice, I just distributed, in a sense, I separated the fraction. I separated the fraction 1/5, 1/5, 1/5. If I take the derivative, it'll be 2 over 5 x plus 3 over 5 plus 0. Looking here to the right, that's 2 over 5x plus 3 over 5. Same answer. All right, so the goal is that if it doesn't look like a problem that we're used to, change it around so it looks like something we're used to. and then you can take the derivative.